Okay, we're about to dive into something pretty wild, a totally new way to think about some of the biggest questions in physics. It's an idea that ties together everything, from the tiniest particles all the way up to the entire cosmos. And it all kicks off with a really simple question.
Now I know, that sounds like the beginning of a weird joke, right? But stick with me, because the answer could genuinely change how you think about, well, everything. I'm serious.
You see, a growing number of physicists are realizing that the universe, whether you're looking at the super small or the unbelievably big, acts a whole lot like a fluid. Yeah, I'm talking about the math of things like flow, pressure, vortices, stuff you'd see in a river, but used to describe things we thought were completely different.
And let me be super clear here. This isn't just some loosey-goosey metaphor. It's a really powerful analogy that's actually backed up by some seriously deep and precise mathematical similarities. So, okay, how does this actually work in practice? Let's zoom way in, down to the quantum level, and talk about one of the most basic things there is, electric charge.
You know, it's a fundamental rule of our universe that electric charge is quantized. Basically, it only comes in these neat, tidy packets. You can't have like half an electron's worth of charge. But why? The standard model of physics just kind of says, well, that's just how it is, but it doesn't really tell us why.
Well, this is where the world of fluids comes in with a pretty amazing parallel. We're looking at something called a superfluid here. It's this bizarre state of matter with zero friction. But you don't need to be a physicist to get the key idea. The math, which is just a result of the shape of the flow, forces any little whirlpool, or vortex, to only exist in whole units. You literally cannot have half a vortex. The geometry of the system just won't allow it.
And this is where the analogy gets really specific. The math that describes one of those quantized vortices in a fluid, it's almost a dead ringer for the math that describes a quantized electric charge. That's a huge hint, right? It suggests that maybe charge isn't just some random property of particles. Maybe it's something that just emerges from the universe's underlying flow.
Okay, so that's the tiny scale. Now let's zoom way out. We're going from quantum packets all the way up to the biggest things we can see, the very structure of the cosmos. Dark energy, it's one of the biggest headaches in all of cosmology. But what if it's not some mysterious energy? What if we look at it through this fluid lens? The idea is to imagine the universe as a giant cosmic foam. And the bubbles in that foam are these huge, empty voids in space. And just like bubbles, they have a kind of surface tension that pushes everything else away.
And again, this isn't just a cool-sounding idea. Physicists actually did the work. They built a model of the cosmic web, the galaxies and the voids, using the real-deal principles of fluid dynamics. They wanted to know, does the math actually check out on this massive scale?
And you're not going to believe this. This is where it gets absolutely mind-blowing. The number you're seeing right now, that's what their calculations spat out for the strength of this cosmic surface tension. And it is an incredibly close match to the real value for dark energy that we've measured with our best satellites. Think about that. A kind of weird, out-there idea produced a number that is dead-on accurate.
Okay, so we've tackled charge and dark energy. Let's get ambitious. Let's use the same fluid perspective to go after the biggest mystery of them all. What is really going on inside a black hole?
Right now, Einstein's theory of general relativity tells us that a big collapsing star crushes down into something called a singularity. It's a point with infinite density, where all the laws of physics as we know them just break. They stop working. But the thing is, nature really, really doesn't seem to like infinities.
So the fluid model gives us this really cool alternative. What if, instead of collapsing forever, the matter hits a kind of ultimate wall, a maximum density, an unbelievable pressure that forces it to bounce back? The singularity just doesn't happen. It gets replaced by a bounce. And the black hole effectively turns into a white hole, spewing stuff back out.
And again, this isn't just some idea from a sci-fi movie. This diagram here, it actually represents a real, exact solution to Einstein's equations that describes this whole bounce process. It's totally valid physics, except for one tiny, tiny quantum moment right at the very peak of the bounce.
So you might be thinking, why haven't we seen this? Well, here's the kicker. From our perspective, way out here, we'd never see it happen fast. Because of the crazy time-warping effects near a black hole, that bounce would take an insanely long time. So a black hole we see in the sky could, right now, be a star in the middle of a bounce, just in super, super slow motion.
So we've got these incredible analogies for charge, for dark energy, for black holes, But what if it's not just an analogy? What if the connection is way deeper, like woven into the very fabric of space-time itself?
Okay, deep breath. I know this looks like a whole lot of jargon. It's pure math, and it looks pretty scary. But trust me, the idea behind it is a game changer. So let's just break down what it's actually saying.
In simple terms, it's saying that the shape of space itself creates the rules. Things like charge being quantized, that might not be a random rule of physics. It might be something that's required by geometry. The universe is shaped in such a way that it has to be that way. The rule isn't some add-on, it's a direct result of the shape of reality.
So we've gone through all this. What's the big takeaway? What should we really remember from this whole universe is a fluid idea?
Well, we've seen how just changing our perspective, thinking of quantum charge as a vortex, dark energy as surface tension, and a singularity as a bounce, gives us these incredible new ways to tackle three huge, separate problems in physics. And they're not just stories, they're plausible, testable ideas.
Look, the big lesson here isn't that the universe is a fluid. It's not literally filled with water. The lesson is about how science works. Sometimes, the biggest breakthroughs happen just by finding the right way to look at a problem, a new language or a new mathematical tool that suddenly makes the complicated stuff feel simple. It helps us find secrets that were right there in front of us all along.
And that leaves us with a really cool final thought, doesn't it? If this one analogy, thinking of the universe as a fluid, is this powerful, it really makes you wonder, what other huge mysteries are out there, just waiting for us to find the right way to look at them? What else is hiding in the flow?